We have lots to talk about. We're going to discuss electromagnetic waves today. That's the subject of this chapter 5. So first we're going to talk about just like classical regular old waves, how they behave, and learning about the different types. And then we'll go ahead and move on and learn about electromagnetic waves, how we talk about them, equations that they follow, and what their nature is. Why do they happen? Okay, so let's do that. The first things to learn are that waves are any disturbance in a medium, such as water, which transports energy from one place to another without causing a permanent change in the medium. Think about a wave moving through the ocean, right? Now, not waves crashing on the shore, but imagine being offshore somewhere in a boat. A wave rolls past you, right? Lifts up your boat. Your boat goes right back down to where it was, and the wave just moves on, right? You pretty much stay stationary in your little boat, right? And the wave moved past you, okay? The wave was the disturbance in the medium. The height of that wave represented the amount of disturbance in the medium, right? You could recognize like a little wave passing under your boat versus a very, very big wave passing under your boat, right? You would raise up a lot more if a big wave passed under your boat versus a small wave. So that's what a wave just is. It's a disturbance in some medium. Okay, now the waves we experience in the ocean are different than sound waves because of the way that they work, but they're the same type of thing, right? A sound wave is some disturbance in a medium. I'm pushing around the air when I talk, right? And waves in the ocean or waves in water are disturbances in a medium. What is suspicious? What I think is suspicious here is that when we say a wave is a disturbance in a medium, then we say which transports energy from one place to another. That sounds suspiciously like another definition of something that we've talked about. What do we call it when energy moves from here over there, moves from one place to another? It's kinetic energy is like the moving part of it, right? But anything which transports energy from one place to another is radiation, right? So there's some relationship between the definition of radiation or what radiation is and then what these things we're calling waves, right? You can imagine dropping a rock in a pond, yeah? And then the waves, the rock hits the pond in one spot and the waves ripple away from that spot, right? Very much like radiation moves and takes energy away from where it starts, where its source is, right? So it's not going to be, it's not an accident that those two things have very similar definitions. Okay, so all right, so a wave's a disturbance in a medium. Energy is transported through the medium, and the medium just goes right back to where it was after the wave moves through it, right? Again, you're in a boat on the water. You raise up, you fall, you go back down, and the wave goes on. Your water that you're embedded in stays right there, right? It doesn't go anywhere. Okay. Two types of waves that are useful for us to talk about: transverse waves and longitudinal waves. Okay, or you can also call them compression waves. Okay. Transverse waves, they wave perpendicular to the direction that they travel, right? So you can imagine, right, got the water level here, right? You're in your happy little boat, okay? And then the wave moves toward you, right? The wave's moving this direction, about to push your boat up. The wave is moving from left to right, yeah? But the displacement of the wave is up and down. Right, the wave pushes the water up and down, but it's moving this way. Make sense? That's why we call it a transverse wave. Okay, the direction of displacement is perpendicular or transverse to the direction of movement. Okay, electromagnetic waves are going to be like that, where they move one way, but the wave is actually going the opposite direction. Okay, so water waves, right, traveling toward the boat, displacing up or down, because in fact the water wave is more like that. More like an up and down wave. Yeah? So it's being displaced upward, it's being displaced downward as it's traveling from left to right and rolling under your boat. Okay? Transverse waves. Direction of displacement is perpendicular to the direction of travel. Longitudinal or compression waves displace their medium in the direction that they travel, right? When I talk to you, I'm sending sound from my mouth towards you, right? And what I'm doing is, as the sound's coming out of my mouth, as the air's coming out of my mouth, I'm pushing and compressing the air in front of me, right? And that pushes and compresses the air a little further away from me and a little further away. The direction of the wave, the displacement of the medium, is the same direction in which it travels. That's for compressional waves. Sound waves are a great example of compression waves, where water waves are a great example of transverse waves. Okay, so we have our two types of waves, okay? We need to focus on transverse waves, not compression waves for our talk today, okay? So our displacement of the medium is perpendicular to the direction the wave travels. So waves up and down as it's moving in the perpendicular direction. These waves are going to have four characteristics, four things that they always have, and these are they'll have relationships between these things. Okay, for example, if one of these characteristics doubles, like frequency, we would know based on equations that something like wavelength would be cut in half if everything else stays the same. So we're going to learn these four characteristics, what they mean for the waves, how we talk about them mathematically, and how they relate to each other. Good morning, Lizette. First is amplitude. Amplitude represents the height of the wave. Okay? Again, you could tell the difference between a little water wave and a very large water wave, right? Those two things, if they were coming toward you, right? Scary. You'd be a little more scared of the big water wave that's taller than your little tiny sailboat, right? And less scared of that little wave that's just going to make the boat move just a little bit, right? Okay. So amplitude represents the maximum displacement of the wave. So the water undisturbed, right, is represented here by this sort of horizontal line, yeah? That's representing the level of the water, all the oceans down below us, and all the skies up above us, okay? So when there's no waves, the water is just relaxed and flat, kind of like where the boat's sitting right now, okay? Then the wave comes through, takes your little boat, and raises it up, okay? The maximum height that you're raised to above that baseline, that's our amplitude. So it's the height of the wave above the baseline, okay? Above where the medium would be undisturbed, okay? The maximum height of the wave, that's amplitude, measured from where it's undisturbed. And as you can imagine, the amplitude of the wave has something to do with the energy of the wave, right? I mean, a little wave is not going to move you very much. And remember, we defined energy. Well, I won't define it. You will. What's the definition of energy? The classical definition that I gave you guys. No, I mean, radiation is a form of energy, but what is energy? Energy has the ability to do work, right? So then you have to, it's a two-part thing, because you say, okay, energy is the ability to do work, and then you have to go, all right, what do you mean work, right? So what's work? Power can do work. So power is a way we can talk about energy. But I'm getting at something here, like movement of massive things, matter, right? Energy is the ability to do work. Work is changing the position, velocity, right? The state of some piece of matter, right? The boat and you on it are matter, right? And if a little wave rolls underneath you, your position and velocity don't change very much, right? You kind of go up and down just a little bit, right? But a big wave in the ocean rolls underneath you and it can topple your boat, right? It's a lot of energy, rather relative to the small wave, it's more energy being put into you, yeah? A wave twice as high is going to put like twice as much energy into you. Yeah, it's going to move your boat twice as high, for example. Okay? So there's a relationship between the amplitude of the wave and the strength of the wave. Okay? So we associate amplitude. Is there somebody trying to get in, or are they unlocking it? It's Andrew. Okay, all right, cool. There's a relationship between the amplitude, the height of the wave, and how strong that wave is. Okay? Similarly with sound, right? There's a relationship between the amplitude of sound and the strength or the loudness you would experience, right? How loud you experience that sound. Okay, that's amplitude. Again, just to give you a cleaner picture, it's measured from where the medium would be undisturbed, such as the flat surface of the water, to the maximum height of the wave. Okay? You ever seen the big wave surfers who surf those, 60, 80 foot or bigger waves, right? They can get absolutely rocked if they fall, right? And lots of energy put into them, yeah? And you can then contrast that against people who just surf the regular old 3 to 5 foot waves that we get off of our coast pretty regularly, right? They can get tossed and rattled too, but much less so, and they have much less of a chance of injury than those people who are surfing the waves that make them look like tiny little insects on the wave, right? The wave is taller. It has more amplitude. That's not the only part of the story, but it's one of 4 parts, okay? Amplitude. All right. That's amplitude. Let's talk about our next thing. Our next thing is wavelength, okay? Wavelength is the distance measured from 2 common points, two of the same points. Like, for example, shown here, it's a measurement taken from the crest, the tallest point of one wave, to the tallest point of the next wave. How far are they apart? That's wavelength. So you stand in the ocean, right? You get hit by a wave. You stand like knee deep at the edge of the ocean, right? And the waves kind of lap on the shore, yeah? You get one wave hits you, and then a short time later, another wave hits you. They're traveling at some speed, right? And they're some distance apart. You're going to be hit by one wave and then hit by another wave, okay? There's distances between those waves. You can imagine that if you were struck by one wave per second, okay, and then the waves kept the same speed but shortened their wavelength, let's say the wavelength got cut in half, you would be hit by twice as many waves per second. There's a relationship between wavelength and the energy that the wave carries. So let me just give it to you. The shorter the wavelength is, the higher the energy. The shorter the wavelength, the higher the energy. If as long as everything else stays fixed, right? We don't change any other numbers. If wavelength gets shorter, energy gets bigger. Remember, energy is the ability to do work. Work is moving things. So with more energy, we move things more easily. Like you standing in the ocean. You get hit by enough waves per second and you're going to get knocked down, right? Notice that we can take a measurement from crest to crest on a wave, and that's wavelength. We can also take a measurement from undisturbed medium, such as shown here on the right, undisturbed medium, to the next undisturbed medium point through one full wave cycle, okay? And that's also wavelength. And they're going to be the same thing, okay? The distance is going to be the same. Doesn't matter which 2 like points you measure from, as long as you measure from 2 of the same kind of points. Crest to crest, trough to trough, undisturbed medium to undisturbed medium, right? Wherever you're taking your measurement from, as long as it's 2 like points, you will always agree. Next thing to learn about transverse waves, this is not one of the 4 characteristics, but it's important to learn. We think about these waves as being a cycle, okay? As displacement upward in the medium, followed by or preceded by a exact same displacement, but in the opposite direction, right? So again, when a water wave rolls through the water, okay, directly in front of and directly behind the wave, okay, that you call the wave, that's the positive wave above the water, will be a depression followed by another depression, a trough followed by another trough, okay? And you see that when we show you pictures like this. The wave has to wave up, positive wave, and it has to wave downward too, okay? We don't just get positive waves, okay? We get positive waves followed by negative waves, displacements downward in the medium, okay? So as this wave's traveling toward you, before your boat is pushed upward, it's gonna drop downward into that trough and then be shot upward, yeah? So the actual amount of movement your boat will undergo is going to be more than just the amplitude of the wave. You're going to be actually moving double the amplitude because you'll be moving down and then up.